Building a better little man computer. Digital Solutions FA1. So what is this technical proposal about? Developed by Dr. Stuart Madnick in 1965, the little man computer is a staple of low-level computer education. This technical proposal will propose an improved web-based little man computer simulator. This proposal will have 6 sections. Constraints and limitations. To adhere to the requirements of the given task, the following constraints must be met. Firstly, it must be a web application. Secondly, the system must contain the components of the von Neumann computer architecture. Users must be able to write programs using the little man computer assembly mnemonics. The system will then convert these mnemonics into bytecode. When running, the system will also need to make use of the 4 system registers. And finally, the simulator must allow for user input and output. Additional constraints on the project include that there is a fixed period of 4 weeks to develop the proposal, and that the presentation must use the EDGE, Explore, Develop, Generate, Evaluate process. In terms of limitations, as a web application, the development languages are limited to HTML, CSS, and JavaScript. Also, as no permanent server-side data storage will be used, the application must store data in its own local storage using the browser's API, or allow files to be downloaded and uploaded from the user's computer. Users. The system will have 2 main users. When teaching students using the little man computer as a tool, James Harris has a number of classroom concerns. This is James Harris's complete persona. Sarah is learning about programming for the first time. Her concerns relate to content overload in the classroom and having to manage too many interactions and ideas at the same time. Sarah faces additional pressures to perform well, both from herself and her parents. After consideration of the users, a number of explicit system goals were obtained and impact models developed. The first goal is to improve algorithmic thinking, then reduce programming errors, and then decrease lexicon complexity. Additional personal impacts for James Harris include a higher level of personal satisfaction from teaching his students and less setup time in the classroom. Socially, he should hear more positive affirmation from students about the subject and increased long-term student retention. Sarah Kim should be able to develop better relations with her parents, as she can grasp what they do for a living and further understand their passions. 2 existing solutions were chosen: Peter Higginson's Little Man Computer Simulator and Microsoft MakeCode for the microbit. Peter Higginson's Little Man Computer Simulator has utility features that allow the user to load and edit assembly programs, assemble and store programs as bytecode, and interact with the controls that assemble code, execute programs, reset the system, and load code from external files. The system also has a speed control and animation to allow tracking of program execution. It also has easily accessible sample programs. The system is only usable on a desktop monitor and has no mobile variant. There are a number of learnability issues with the application. The help page begins with an announcement about another system and a changelog. Users cannot therefore easily find guidance. The instructions provided are only text-based, and no diagrams or screenshots are included, so new users struggle to understand the system. Additionally, the system does not explain the meaning of the different mnemonics or give an explanation about the provided algorithms. According to Google's Chrome Lighthouse analysis, this little man computer simulator has sporadic success meeting the Web Content Accessibility Guidelines. These include the orientation is locked to a horizontal presentation. The system should be able to use vertically on different screen sizes and orientations. Thus, it fails to meet WCAG 1.3.4 perceivable orientation. The system also uses text output to inform users of errors, adhering to WCAG 3.3.1 error identification. This provides user safety when working in the application. However, WCAG 3.3.3 error suggestion is not met, as only the location of the error is identified and no recovery options are presented. Microsoft MakeCode Editor for the microbit is a tool that allows the use of block, JavaScript, and Python programming language to program a microbit. The user interface is very effective in an educational context. The system provides safety through hints and debugging information, and also provides a working simulator. The Little Man Computer assembly language uses a 3-digit opcode structure. The first digit represents the operation, while the last 2 digits represent the memory address or data. After considering all content covered thus far, the system has the following functional requirements. These non-functional requirements, and these technical requirements. Notably, as different browsers can operate in different ways, the application will need to be tested across numerous systems. In an educational context, the system may be used across a large range of devices of varying screen sizes, so the interface should be responsive. For this proposal, however, the most common educational device of a student laptop will be designed for. These are additional technical requirements. Success criteria. To be successfully developed, a Little Man computer simulator needs to meet the following success criteria. The system is being based on the following assumptions: that we are not developing for a mobile phone device, as learning most likely occurs on a desktop, laptop, or larger screen device like an iPad. That all devices will have adequate network speed and bandwidth, and that some, but not all user devices will have a touchscreen. This is the proposed interface of the Little Man computer simulator. On the home screen, users can choose a tutorial, open an existing local project, or upload a saved project from disk. Additionally, users may select the plus symbol to start a new program. When loaded, the interface is in block mode by default, and all the registers are set to 0. Users can add blocks to the program by dragging them across to the edit window. As further commands are added, the live conversion to bytecode occurs. Incomplete commands are highlighted in orange, providing a visual cue for safety of a potential error. In the memory array, errors such as a missing halt command are red, warnings are orange, and when running correctly, executed commands are green. This use of color mirrors the commonly understood traffic light system. The interface uses color and proximity in the block list to group light commands. Changes in background color make it easy to distinguish between the block list and blocks being used for code. Output from the program is shown in a sidebar that is extendable from the right. This can be opened manually by the user, but it will auto-open if a program is running and it is required. Program halts are also indicated in the sidebar region, as well as by red highlights in the bytecode array. When the user changes mode, the system transpiles code to text. This functionality will also work in reverse. Line numbers are provided for understandability and teaching instruction. Significant space between lines and capitalization is used for perceivability. The currently selected mode is highlighted in white, contrasting the rest of the header of the page. Selecting the question mark opens the help screen modal. When utilized, the application will generally operate in this manner. When the application is loaded, the user is presented with the home screen. Selecting plus opens a blank program. In this demonstration, a program that adds two numbers together will be written and executed. Dragging the input block updates the memory array and shifts the phantom halt command across. Selecting the store command adds it to the sequence and updates the memory array, this time with a warning which goes away when the user adds a value. Let's store the data at location 99. Adding another input, and then the addition command, which will also be set to 99 as well. Then adding output, and finally halt. The phantom halt command now disappears. It is now time to execute. Selecting the run button, let's input 7. Submit. And let's add 12, so we can expect an answer of 19 at the end. Submit. And here we are. Our program worked as expected. After execution, we can reset the system, and now the registers are zeroed and the progress indicators are gone. We can switch to text mode. Altering the code will generate error prompts, and hovering over the middle blocks will render a pop-up with programming assistance. Selecting the question mark help icon in the top opens the help screen. We can also select the gear wheel for settings, and if desired, make changes. And finally, selecting home will turn us to the main interface where our project is listed. This concludes the presentation for a newly educationally focused Little Man computer simulator. Thank you.